Okay, welcome back, folks. Here we go. We're going to be talking about strong acid-base titrations. So remember, a titration is a way that we can determine exactly what we have in an unknown. So typically, the way this works is we have our burette. Okay, all right, we've got our burette. It can be filled with acid or base, but in this scenario, we'll fill it with base. Okay, and we will have our flask, all right, with some acid in it, all right, and we will be adding base to neutralize the acid. All right, in this case, remember, we're always going to add an indicator uh, to help us observe a reaction. All right, and the indicator needs to change color at the equivalence point. Okay. You're probably like, well, what's the equivalence point? Well, right here is the equivalence point. I'm going to make it in this nice purpley color because we'll use phenolphthalein a lot of times. Remember, phenolphthalein got that like pinky color, okay? And it's the point in the titration when the moles of the acid, the H plus, equal the moles of OH. So when we're adding a strong acid and base together, the pH at the equivalence point will be 7. Okay, it'll be 7. All right, the end point in the reaction is when the indicator changes that color. Okay, changes color. So if we were to draw this scenario here, if we were to draw a titration curve for a strong, this is called a strong titration curve. Okay, so if we were to put a pH meter in our solution here, okay, all right, measuring P is the pH, okay, and we're going to have milliliters of base added on the x-axis, and if we had a pH meter in our solution over here in the acid, right, it's going to start out pretty low, probably around 1, all right, and slowly but surely it will come up. And then as we get real close to the point where the amount of H plus in solution equals the amount of OH minus in solution, a very small amount of base will change, all right, our pH. And then ultimately we reach the equivalence point here, all right, at 7 for a strong titration. And then it will start to level off again around 13 or so, 12 or 13. Okay, so and we're hoping to see that color change right around that equivalence point. Okay, we need to choose the right indicator for that. Okay, and so doing these calculations for a strong titration, doing some of these examples, is pretty straightforward because it's a lot of just stoichiometry and looking at it using stoich and calculating new concentrations and stuff like that. Okay, so let's roll through a couple examples here. So here's kind of a classic example. We have a 37 milliliter sample of sulfuric acid, and it's neutralized by 23 milliliters of a 0.16 molar sodium hydroxide solution. Okay, so our sample is in our flask here. So we've got 37 milliliters of H2SO4, all right, and our base was in our burette, and we've got 0.161 molar NaOH, all right, and we added 23 milliliters there, okay? So we know all of the information about the NaOH. That's our known. Our unknown is the sulfuric acid. We don't know what the concentration of that solution is. We don't know what this concentration of SO4 is. That's why we're analyzing it. Okay, we don't know what that is. All right, so let's write a balanced equation for this reaction. We've got H2SO4 and sodium hydroxide going to, right, sodium sulfate and H2O, right? And if we were to balance this equation, we would need 2 sodium hydroxides, right, for every 1 sulfuric acid. So it's not a 1-to-1 mole ratio in this case, and a lot of times it will be 1-to-1, but this is one of those examples that it's not. Okay, so that's why I wrote out a balanced equation here. So we can write out a balanced equation to kind of check up on things, just to make sure, because we're probably going to set up some ice tables and things of that nature as well. But here we are. So we got to start our calculations here, what we know everything about, because we want to get into moles. We need to know moles of base we added, right? Because then that will tell us how many moles of acid will be in there, because that's what we need to know. We know the volume, right, of acid. We know that our original sample was 0.037 liters, but what we need to find is the moles of H2SO4 in that solution. So we're just going to use some stoichiometry. We know we have 0.023 liters of 0.161 molar sodium hydroxide, NaOH. So that's 0.161 moles per 1 liter. And we just need to find moles of H2SO4. So all we got to do is use the mole ratio, right? We know there are 2 moles of sodium hydroxide for every 1 mole of H2SO4. All right, if we run that calculation, 0.023 times 0.161, divide that by 2, we end up with 0.00185. Okay, and in order to figure out the concentration of sodium hydroxide here, we just got to plug that in. We got 0.00185 moles H2SO4 divided by 0.037 liters. And we end up with 0.050 molar H2SO4. Okay. All right. So that's the first example. Next example here, we've got a solution of sodium hydroxide, and we're standardizing it, meaning we're just reacting with potassium hydrogen phthalate, so KHP. Okay, so we'll use KHP in the future. So this is kind of the way this works. This is an interesting. Sodium hydroxide is our base here, and we're going to react it with KHP, and it's going to act like a strong acid. And here is its formula in here. I'm going to write it just a little bit different. Okay, I'm going to write it a little bit different. I'm going to write it as HCH4KO4. Okay. All right. So, and the way that works is it's going to form water, H2O, and sodium, like sodium phthalate. Okay. So, which also floats around in solution. It's just dissolved in solution too. That's kind of the way it looks right there. Okay. We're going to react on a 1-to-1 mole ratio. All right. So they give us the formula weight for KHP there, and the mass of KHP used in the titration was 2.54 grams. So before starting the titration, you read 0.323 milliliters, and after it read 33.7. Okay. So from this data, we want to calculate the molarity of the NaOH. Okay. All right, so what's going on here is, so just so we can visualize this, in our flask we have 2.54 grams of KHP. All right, so what we know in here is we know the moles of KHP. Okay, we can figure out the moles of KHP. And in knowing that, we know that we react in a 1-to-1 mole ratio. So if we know the moles of KHP, and we know in our burette, okay, we know this is the NaOH here, okay, we know the moles of KHP at the equivalence point equal the moles of sodium hydroxide at the equivalence point, okay, after all of it's been reacted. And we also know that it went from 0.23 milliliters down to 33.07 milliliters. We know the volume of the NaOH solution. So once we know the volume, hey, we have moles per liter, okay? So we're going to use our KHP, 2.504 grams. Put that into moles. So 1 mole of KHP is 204.2 grams. And we know the mole ratio between NaOH and KHP is 1-to-1. So now we know the moles of NaOH. Okay, and since we're trying to figure out what the concentration is of the NaOH solution, remember concentration is moles per liter. We know we had 0.00123 moles of NaOH. And we just need to figure out what the volume of that solution is. So 33.07 milliliters minus 0.23 is 32.84 milliliters. So we just need to put that in there. So we have 0.3284 liters. And that gives us 0.37. 0.03745. We'll split the difference between the sixths there. Okay, so 0.373. All right, molarity. All right, we'll do one more example, and this is where we'll use an ice table and stuff like that, and that sort of thing. So here we go. So the next example is kind of an interesting situation that they'll have us do from time to time, okay, and that sort of thing. So they're going to want to know what the pH is at different points in the titration. Okay, so in this case, we are titrating 50 milliliters of 0.2 molar nitric acid, so HNO3, with sodium hydroxide, NaOH, right? And it's going to water and sodium nitrate, right? So it's a 1-to-1 ratio here. We got our formula. So if we were to just write this out in terms of a net ionic equation, be H plus and OH minus going to H2O. Strong to strong titration here, 1-to-1 ratio. So this will be a fun little ice table to make when we have to do that. Okay, first thing I want to know is what's the pH when no hydroxide has been added? So that's easy enough. We know that the concentration of our HNO3 is 0.200 molar HNO3, right? It's a strong titration. It's a strong base or a strong acid. So pH is equal to negative the log of the concentration of H plus, which is equal to negative the log of 0.2 molar, which is equal to log of 0.2, 0.699 for our pH. So we haven't added anything, 0.699. Okay, great. All right. Well, next thing, they want us to, for the equivalence point, okay, calculate the volume of base needed to reach the equivalence point. So remember, at the equivalence point, pH is going to be equal to 7. Okay, pH will be equal to 7. And it's also the point at which moles of acid equal mole of base. So all we need to do here is do a little stoichiometry. Okay. We got to figure out how many moles of acid we got in solution. So we got 0.05 liters. We know there are 0.200 moles of HNO3, 1 liter. So we're using the molarity, get into moles. We're going to do the mole ratio. 1 mole of HNO3 will react with 1 mole of sodium hydroxide. So we did our mole ratio. Now we're out of moles. And we're going to use the molarity as well here to find out how many liters of base we added, or of base are added. So we know the concentration is 0.1 molar. So that's 0.1 moles of sodium hydroxide for every 1 liter. So if we do the work here, we do that calculation. So 0.05 times 0.2 divided by 0.1, you end up with 0.100 liters, which is 100 milliliters. Okay, so we added, so we would need to add 100 milliliters of sodium hydroxide, neutralize all of our 50 milliliters of 0.2 molar HNO3. And that makes sense, right? Like the concentration of the strong acid is twice that of the base. So we're going to need twice the volume of the base. Okay, so it's 100 milliliters. And the pH at that point is 7 because it's the equivalence point. Okay, all right, and yes, that's correct. Okay, so now what they want us to do is they want us to calculate the pH when 20 milliliters of NaOH has been added. So we got to figure out, well, how many moles of OH do we have to start with, and how many moles of H, well, how many moles of H we have to start with, and how many moles of OH we added. Okay, so we're going to draw a little ice table and then go from there. Okay, so and we're just going to look at H plus and OH minus, because that's all we really are interested in, because we want to find pH. H2O is a liquid, so it doesn't matter. So if we do our ice table here, ICE, okay, we don't care about water, it's a liquid. And first thing we need to do is figure out the moles. We're going to operate in moles here for our ice table. We're going to operate in moles for our ice table. So for H plus, we know 0.05 liters, and we have a 2.2 molar H plus solution for 1 liter. So that means that we've got, what's that, 0.01? 0.05 times 0.2. Yes, 0.01 moles. We have 0.01 moles of H plus to start. And we added 20 milliliters of the 0.1 molar NaOH. So that means we got 0.02 liters times 0.1 moles of OH minus per 1 liter. So that means the amount of OH we added was 0.002. So that's where we start off initially. Obviously, see that OH minus is our limiting reactant. So minus 0.002 minus 0.002. We get 0. We have no OH left in solution, but we have 0.008 moles of H plus left in solution. And we need to know what the concentration of H plus is in solution, right? We know that there are 0.008 moles of H plus in solution. And what's the new volume of our solution? Well, we start with 50 milliliters. We added 20. So now we have 0.07 liters. So 0.08 divided by 7, we have a new concentration of 0.114 molar for H plus. So pH is equal to minus the log of the concentration of H plus, which is 0.114 minus the log of the second answer. Our pH is now 0.942. Okay, so there we go. All right. All right, well, let's figure out, after we add 100 milliliters, what the pH is. Well, wait a minute. Didn't we just do that? Remember, up at the equivalence point up here, we already worked. They asked us for the volume of base needed to reach the equivalence point. Remember, it was 100 milliliters. So, okay, great. So that's awesome. So pH at this point is equal to 7, all right, because it's the equivalence point. Moles of acid equal moles of base. So all we got in solution right now is H2O. Okay, that's all we got. So at that point, I mean, after 100 milliliters, right, we've added 0.01 moles of OH. So all we have is water floating around in there, right? So all we got is H2O. Okay, so that means that it's Kw, right? Is equal to H plus. And just to prove it to you, we could work it this way: OH minus, right, is going to be equal to 1 times 10 to the minus 14. It means both of those equal 1 times 10 to the minus 7. All right, so all that sort of thing. All right, so finally here, they're going to have us. All right, well, what's the pH when we added 200 milliliters of NaOH? All right, well, let's run our ice table here. H plus OH minus go into water. H2O. All right, well, let's see. All right, so initially we got 0.01 moles of H plus. If we had 0.2 liters of 0.1 molar hydroxide solution here, that means we just add 0.02 moles of OH. OH minus. We have 0.02 moles of OH initially. No. All right, well now our limiting reactant is H plus. So minus 0.01, minus 0.01. This is H plus is 0. Now all we have floating around in solution is hydroxide ions. So now our pH is really determined just by the concentration of OH minus ions in solution. So we got to figure that out. All right, so we've got 0.01 moles of hydroxide ions flowing around. What's our new volume? Well, we've added a total of 200 milliliters, and we started with 50. So that means our new volume is 250 milliliters, or 0.25 liters. So 0.01 divided by 0.25 is going to be equal to 0.04 molar. So POH is equal to minus the log of the concentration of OH minus in solution. So we have a POH of 1.39, well, basically 1.40, because that's 1.3979. And remember, pH is equal to 14 minus the POH, which is 1.40, which is actually 12.60. There it is. Awesome. Okay. So, yeah, so that's what we're going to be doing with some of this stuff. Here's another one, except now the ratio is 2 to 1, okay, in terms of you're titrating with acid, but also got twice the volume, but you got to be careful with our 2-to-1 ratio here, okay, and you guys can work through that one on your own, all right, but it's a good one to work through. All right, I hope you guys are having a good day, and we'll be talking to you soon.